Japan built a wall so enormous that it stretches for hundreds of kilometers along its coastline. In some places, it towers over entire towns. It cost billions of dollars, and it was built for one reason: to make sure what happened here in 2011 never happens the same way again. On March 11, 2011, a magnitude 9.0 earthquake struck off northeastern Japan. 6 minutes of violent shaking triggered massive tsunami waves, with run-up heights climbing 40 meters inland. Neighborhoods, ports, and entire fleets were swept away. More than 15,000 people died as existing seawalls failed. For the people behind these defenses, the failure was not theoretical. The water crossed the barrier, reached the town, and kept moving. In response, Japan launched a $12 billion, 400-kilometer defense program. But how do you protect hundreds of kilometers of coastline from something powerful enough to move entire buildings? Can Japan actually build a wall strong enough to stop the ocean? In Miyako, a 10-meter concrete wall faced a wave exceeding 15 meters. The ocean swept straight over the crest, but the true disaster happened on the landward side. As the torrent poured over the top, it violently clawed at the soil behind the barrier. This fast-flowing water carried away the supporting earth, a process known as score. Stripped of its backing, the concrete cracked and collapsed. At Kamaishi, water forced its way through the sea floor, washing out the rubble foundation under massive concrete blocks. River inlets and harbor openings became pathways for the surge. The front of a seawall isn't the only part engineers have to protect. You can't build a wall capable of surviving a tsunami until you first build a foundation capable of surviving the ocean. But the most important part of the wall is the part nobody sees. The concrete structure towering above the beach is merely the exposed tip of a massive underground anchor. In areas with soft sand and marine clay, engineers cannot simply pour concrete on the surface. Instead, they drive giant steel sheet piles and bored concrete columns 30 to 60 meters deep into the earth, securing the barrier directly to the solid bedrock. These deep piles must hold the wall upright against two massive simultaneous forces: the violent vertical shaking of an earthquake and the immense horizontal impact of a tsunami wave. But anchoring the wall is only half the battle. Engineers now face the monumental challenge of fitting these massive, rigid foundations along a coastline that is anything but straight. The Sanriku coast bends through steep coves, river mouths, and sandy beaches. Because of this, the project could not be one identical structure repeated along a straight line. Every single segment had to be individually surveyed, custom-shaped, and aligned to fit its specific terrain. Where sheer cliffs made normal road access impossible, contractors built temporary cofferdams and used specialized heavy cranes to lower massive prefabricated concrete modules into place. Surveyors, crane operators, and local engineers had to tailor every joint. The wall's apparent uniformity conceals thousands of separate local design decisions. But as these massive concrete blocks finally rose from the shoreline, they raised a new question: should a wall facing a changing ocean be completely solid? To break the ocean's brute force, engineers place interlocking multi-ton concrete blocks called tetrapods in staggered rows before the main wall. These structures don't form a solid barrier. Instead, their four-legged geometry leaves open spaces between the units. When a giant wave hits, water is forced into these narrow gaps, creating violent, chaotic turbulence that dissipates up to 30% of the incoming energy. The gaps aren't a weakness, they're part of the defense. But while this armor reduces pressure on the concrete face, it cannot seal the coastline's most vulnerable openings. A seawall cannot run continuously across every river, harbor, road, and navigation channel. Yet these necessary openings create perfect pathways for a tsunami. To close these gaps, Japan integrated 443 automated floodgate units directly into the barrier. When an earthquake strikes, seismic sensors detect ground acceleration and trigger an automatic shutdown within 30 seconds. High-pressure hydraulic cylinders drive the steel plate gates down. If the main power grid fails, elevated backup battery banks and diesel generators instantly fire up. In a worst-case scenario, emergency hand-wheel gearboxes allow manual override. The entire sequence is a high-stakes countdown: detect, trigger, drop, and seal before the wave arrives. Because a defense system is only as strong as its open gates. This shifts the challenge from physical construction to real-world reaction. Can these gates actually hold under extreme pressure? To prove these barriers can survive, engineers blast scaled designs in massive wave tanks and run supercomputer simulations of tsunami flows. But the real test happens underground. A silent network of embedded sensors monitors the wall's health, tracking strain, the internal deformation of concrete and settlement, the gradual downward movement into the sandy shoreline. So far, settlement has remained under 5 centimeters, an exceptional result. Yet this continuous monitoring is not a permanent safety guarantee. It is simply an early warning system to identify structural deterioration before the next massive wave strikes. Rebuilt wall heights vary by location, with major sections standing 12 to 15 meters high. But numerical models show that an extreme run-up can still overtop the concrete crest, especially in narrow bays where coastal geography violently amplifies the surge. Water may pass over the wall, even if the foundations, armor, and gates remain entirely intact. This wall is not a promise that the ocean will stop. It is a machine for reducing force, slowing the water, and buying time. Studies estimate the system buys roughly 10 to 15 minutes of additional evacuation time, allowing residents to reach stairs, marked routes, and vertical shelters. The goal is not to give people permission to stay. The goal is to give them more time to run. Japan didn't build 400 kilometers of concrete because it believes it can control the ocean. It built them because when the next great tsunami comes, even a few extra minutes could save thousands of lives.